Welcome everyone, and thanks for coming to this Tech Talk. My name is Jörgen, and I am very pleased to have Bengt Gustafsson here today to talk about Podcars. Please give him a warm welcome.
Thank you all. So I'm Bengt Gustafsson, and I'm the CEO for a very small startup company in Sweden called Beamways. And I've come here to show you a little bit about Podcars and what they can do for transportation in this new era when we have a few problems. And I think these are maybe the worst problems we're facing. And one of them is the climate crisis, where the cars are, if not the largest source of GHG, which I think they are, they're for sure the hardest to replace. And we'll also have a problem with actually not having enough oil for our cars very soon. The International Watch Board for this says we have 15 years at current rates, 15 years only. And of course, with a lot of cars, we also have problems with congestion in the streets. And it's hard to do something about that because there's no more land. So, one thing that's been tried, and tried a lot here in California, is to build more roads for all this traffic. And now it's kind of full, I think, here. And then you go to elevated roads or dig tunnels, and you have the big dig in Boston. That's the most expensive infrastructure project ever. So I don't think people like tunnels so much for the price. Elevated is also expensive, of course. So, and even if that wasn't true, it goes against our goals. It increases the oil use, it increases the greenhouse gases rather than the other way around. So that's not good. Next thing we could try is to use something else than gas in the cars. And what has been done in 2 countries in the world, that's Sweden and the USA, is to bet on ethanol. And I think that's a bit working less and less well now. We can see that the biomass will not last very long, or to a very large percentage of the vehicles. And we see already that they cut down the rainforests and other types of valuable biotopes to get land for all of these growing of corn or sugarcane or whatever. And this has already been shown to lead to food shortage, although it's not the only reason for food shortage at this point. And so the ethanol people say, okay, we go for the cellulose because that's not something you eat. The problem with using the cellulose is, of course, somewhere all of the fertilizer stuff that's in the ground goes, and it goes into the cellulose. So if you remove the cellulose from your grounds where you harvest this, you won't get many years before the soil is arid and not useful. And also erosion of the land is about 100 times higher if you use the cellulosic part of, in the particular sugarcane case. So, does not increase the mean speed is, however, the problem with this in our big 3 problems on top. So I wouldn't say this solves a big part of our transportation problems. And the car industry, having realized this, they couldn't fool the governments anymore. They turned to the next step, which would be batteries or fuel cells. And batteries is coming along quicker than fuel cells, but it's still a few years away. But the problem is when you roll out a large fleet of lithium battery-powered vehicles, you will find out that there's very little lithium on the planet compared to what you need. I don't know why this is so little known. Anyhow, there are other battery chemistries like zinc, oxygen, but not much effort is going into developing those, which also puzzles me. And fuel cells, some call it hydrogen, and hydrogen is supposed to be the most abundant power source. The problem is that it's bound in water, and you need to split the water first, and that takes a lot of energy. So in fact, it's just a very wasteful type of battery. The only advantage of this type of battery is you can recharge it very quickly compared to a normal battery because you just pour more hydrogen in the tank. But the problem with the hydrogen storage is very high also because you have no good ways of storing hydrogen. You can cool it to near 0 K, which takes a lot of energy, or you can compress it, which takes a lot of energy. So all of these inefficiencies add up to around 30% efficiency from electricity to the wheel. So that's much worse than batteries, if batteries could be found. But however, all of these disadvantages cured, it would not increase the mean speed because we still have the congestions in all our streets. And most traffic planners think that we can solve this just by adding transit. And if any one of you lives in San Jose, you know there's a really nice tram line there. There's only one problem: no one rides it. So they have actually $60 per passenger in subsidies from the city. $60. And why don't people travel in the trams? Because it stops at all stations. You get like 10, 12 miles per hour mean speed. And that's along the line, and you don't want to go along the line. You will go between two other points. So you have to change to another line if there is one. And I would say in the US, it's seldom that you can find a reasonable route on public transit. And even if you do, you have to do multiple changeovers. And to build more of this transit would, of course, relieve the situation somewhat, but construction of a tram line is very costly and very slow because you have to dig up the street, you have to reroute all the traffic, you have a long planning process to be able to do all of this. And even if you do, it doesn't even pay for its own operation from the ticket fares. So the more people ride it, the more losses for the city. So anyway, of our main goals, it doesn't increase the mean speed. In fact, it decreases the mean speed, even for the drivers, because you take away lanes from the streets to allow the tram lines. So, no good. At this point, traffic planners and others, they are a bit confused because they didn't have any more tricks in the bag. And what we think in the very tiny Podcar community is that we have the key to solving all of these local or regional transportation problems. And what are then Podcars? It's an attempt to unify the advantages of transit with the advantages of the car. And the main advantages we take from transit is the electricity power source. And the vehicle is not owned by the person, it's owned by the operator. And thus you can share vehicles. You need to build like 1/10 of the number of vehicles as you would with cars because they're used by multiple persons during the same day. Also, of course, It reduces the oil dependency by reducing the number of car trips that are necessary. And as oil prices go up, of course, more and more pressure will come on other forms of transportation. And people don't want to reduce their mean speed to the bike or tram speed. They want to go as fast as you can go in a car. So what we do to achieve that is to take the individual ride part of the car and the possibility to go anywhere you want in the network of roads. And thus we increase the mean speed compared to transit because of no stops, no changeovers, and compared to car traffic because of no congestion, or at least a very controlled type of congestion where you only have to reduce speed somewhat, not this haphazardly occurring congestion situations you have on the road. So what are Podcars then? Podcars, and I should mention that this was called PRT for Personal Rapid Transit for a large number of years. It's no new invention. It's been around since the 60s at least on the conceptual and test track level, which we will see soon. It has small light vehicles, so you don't have to share your vehicle with any other person unless you're traveling with more people. Typically, it can be 3 or 4 people maximum in these vehicles. And this means that the vehicle total weight could be like 500 kilos for the vehicle and 500 kilos for the passengers. We also enable everyone to go, even if you have a wheelchair or if you have a kid in a trolley, if you have a bike, you can get into these vehicles. And to the right, you can see the first rendition of the Beamways vehicle at the top, and then another vendor at the bottom. And you can see that there are 2x2 seats in the top one, and 1 sofa with 3 seats in the bottom one. And these are the main configurations. So how could we reach some capacity? We need to go very often on the track. We need to go at least every 3 seconds. And if you say this to a transit person, they go through the roof because they're really anything below 1 minute is impossible in transit. So then you have to nudge them and say, okay, what about the freeway? There you go at 80 miles per hour on a sunny day. And you still have 2 seconds between vehicles. And these are automatic. There's no cellular phone calls to the driver during that period. So how can we achieve automatic vehicles with short headways, and how can we achieve very little land use? Of course, we need to go up in the air. That's a prerequisite for this to work, because there you're not competing with other types of vehicles which are not automatic, and you're not competing for the land. And if you remember previously, all vehicles are small. It's a maximum weight of 1 ton, meaning that you can make a guideway here which can only support 1 ton vehicles. This is very different from a roadway where you have to support 60-ton trucks plus some bonus for the overloads they have. And thanks to this, we can also have a rather long distance between the posts. And it's made of steel. I've seen someone trying to make it of aluminum, but I would doubt this should work, but typically it's steel. And one very important thing is that all the stations are on an extra sidetrack, as you can see at the bottom of the lower picture there. This allows the other vehicles to pass anyone who likes to stop at a certain station, and this is how the line speed can be kept up. All of these concepts, of course, are stolen from car traffic. The difference and the drawback compared to the car, of course, is that you need to go to your nearest guideway by foot. or bike possibly. But typically you would have a 300 meter, that's 1,000 feet walk. That's just good for you. You can also add value to the system by, for instance, using it for goods or waste removal. And we call that virtual networks because they wouldn't go onto the same set of station. That's a separate set of station, another type of vehicle, but it's the same network of guideways. To control all of this, we need to have a multi-tier control and operational software, and of course communication hardware, which is redundant and very safe. This is typically done in a way that each vehicle has sensors for the previous vehicles and tries to keep the distance. And of course we have on-demand traffic. I didn't mention that, but typically there are always vehicles available at the station when you get there. So you just jump in the first vehicle and you're off. You never wait, which is not true because typically you would wait 20% of the times you would wait 1 minute. That's according to many different simulation programs. So that level of waiting, which is not very much. So each vehicle goes its own route to the destination. Just look at the top drawing there of the network. There are multiple paths to go. And of course, each vehicle steers itself to where it wants to go. And when the network grows, this also provides redundancy just in any other computer network. So if one of these gets blocked by a vehicle, you can always go around. This is not true, of course, for tiny network like this one we offered for Santa Cruz. But as the network grows, you get the redundancy you would want to have. Nevertheless, you need to have very reliable vehicles, of course. So what the centralized control does is, of course, all the things around it, the ticketing function, the entertainment functions, the advertising functions, but most of all it does the centralized load balancing, or regional at least. So it tells the vehicles, there is a slight queue over here, so please go that way, although it's a bit longer. Accident prevention, of course, is local. You don't want to be relying on being able to communicate with the central control all the time. That's a rather slow communication channel comparatively. And of course, as I said before, rerouting. So we have the basic framework for Podcars, but within this there are so many ways of doing it, and most of them have been tried actually. You can have the vehicles on top of the beams or under it. You can have single direction lines as in the top drawing here, or double direction lines as in the bottom drawing. You can have rotating electric motors or linear motors. And if you have linear motors, you can have them in the car or in the guideway. And you can have batteries, you can have a power rail, you can have a fuel cell actually, if you're in that way. The steering and switching, of course, is very critical because this has to be very reliable and has to be inside each vehicle. And there are so many ways you can do this with different kinds of wheels or extra magnets that just suck you into one of the walls. And there's also the other variety, which those guys don't even want to call themselves Podcars normally. It's called dual mode, which means you can get off the guideway and it's also a regular car at the same time, an electric car. So this solves actually the 300-meter walk problem. But there are drawbacks, of course. You need to have a crash-worthy vehicle, which means it It's probably going to weigh 1.5 ton empty. So the guideway weight is doubled. And you need to have the high reliability, although this vehicle could have been bumped into in the street before. So what are the actual benefits and disadvantages for the passenger? Of course, the big benefit is that you get a car-like service level, except for that little walk. You get a high mean speed, and if it's congestion in the streets, you get a higher mean speed than with a car. And accidents. This country kills 40,000 each year on the streets, and maybe 5 would be killed in this type of system, because so many accidents are driver-related, and in this case, even if it's vehicle-related, we do have multiple safety functions to avoid crashes. And you also get benefit economically by, often reduced number of cars per household, because the mundane commuting can be done with the Podcars, and you can use your SUV when you go actually into the countryside. Oh, sorry. I mentioned the walk. You can't have stuff in the Podcar, of course, as you can have all stuff lying around in your trunk for years. And the vehicle size is, well, that's the same as the car. You have one size. For the society, there's another set of advantages and disadvantages. One advantage for all of us is the reduced emissions. Another advantage for the city is that you can remove the subsidized bus and tram systems and save money and save street space. And in this case, it's very obvious that you would not have to subsidize the operation of this, because the operating cost is very low, so you can take that from ticket revenue. And this is very important. Reduce the parking areas, and in the long term you could reduce the number of lanes in the roads possibly, but parking could go quite quickly when you have Podcars to a certain area. And this is a great value for land developers. Land is expensive, and for instance in San Jose, half of the land is devoted to the car. So if we just can reduce that by a little fraction, that would be lots of dollars. And noise levels should be, of course, much lower than for a regular car, and it's controlled in a better way. But the key point, I think, for communities is this is a much cheaper way to add more transportation capacity than trying to build elevated roads or tram lines or dig down tunnels or tear down houses to build another lane. The problem is that, nevertheless, it's a large investment, and technology has not been proven, and this seems to be the major one for communities. And you need a large network. You need to be able to go where you want to go within the system. There's no standards so far. Everyone makes their own type of system, and communities want to have a diversity of vendors with compatible products, of course. That's going to be in the long run. And then we have the visual intrusion of the guideways as a negative, at least in central areas of the cities. And in Europe, this is a very big issue. In the US, it's not that big. I don't know why. So, as I told you before, the history of this goes back to the 60s, and the first actual systems were early 70s. I'm going to show you, just for fun, a few films taken in this period. They're around 1 minute each. This is, no, wrong button. Sorry. This is the Aerospace Corporation down in Pasadena. They made a test track, and this is a scale model. And you can see the level of technology they had at their disposal at this time. This is the vehicle. That's a 1 to 10 scale model. As a wire wrap boards full of primitive digital circuits. And that's the linear motor down here. Power pickup and wheels for suspension. But despite this primitive technology, they could do nice things with it. And that was the switch. And the switch is magnetics. As I told you before, it sucks the vehicle to one side by turning on one or the other magnet there. And they had somehow programmed these, probably hard-coded in the logic to do certain maneuvers on the tracks like this. And this is, as you can see, a very short headway. They're almost touching. And I don't think that would have been safety approved at that point, and I'm sure it would be safety approved today. But this project is really impressive. This was built in Germany in the late 70s. And as you can see, this test track, it's still a test track, but it's a bit larger. It has 6 stations. It has 24 vehicles. And as you can see, there are different vehicle sizes. And here is the main trick of the system. Some vehicles go under the beams, some vehicles go on top of the beams. Of course, this gives you a dual direction system with just one beam. The problem is that the same vehicles can't go in both directions. So actually you have 2 disconnected systems. And I've not been able to figure out what this actually means in terms of capacity and performance. So here's the hanging type of system. And of course they had all the station stuff, they had the ticketing functions, all of that. This was ready for deployment in cities. In 1978 they had the safety approval. And then the US government told the German government, uh-oh, you must spend all of your research dollar on, or D-marks, on weaponry, on military research. You're not allowed to do any. This was at the height of the Cold War. So they pulled the plug on this project at this stage. But this is the only time a suspended system has been approved for traffic with passengers. Now this one, which is the last one I'll show you of the old ones, this one is actually in operation. Maybe one of you have been at the West Virginia University in Morgantown. There they have this, which they call the PRT, but there are 8 seats in each cabin, so theoretically it's called the GRT, Group Rapid Transit. So how do they do this? When you get to the station, you select your destination, then you have to wait just to see if another passenger comes around with the same destination within a certain number of minutes. If not, you're off, and then it goes directly to your destination. You never stop in intermediate stations. So this proves most of the Podcar concept. The only thing it doesn't prove is the possibility to go different direction, because it's a straight line with 5 stations. a lot of activity was going on. No, I had another one. This is second generation, so to speak. This was in around year 2000 in Chicago. And, oh, sorry. Oh, very sorry. Maybe you can do this better, but I don't know. I just bought this today. Where is the actual? Oh, I skipped that. It's another film. It's on the YouTube, of course. We had other systems. We had the Aramis in France, which was very advanced. In 1973, they ran vehicles with 1 decimeter spacing. That was a laser guidance between the vehicles. They never got it through the safety approval, though. There was some other ones. The CVS system, which you can see to the right, was a rather large test track, several stations, lots of vehicles. Also got a no-go for that project. So, but all the time, small ventures have been boiling beneath the surface, and now we think that this market can actually take off. And this, as you can see, there are lots of vendors around. There are even more than these, but these are the most promising, I think. And Ultra, the top one, already has an order. They're delivering vehicles right now to Heathrow Airport in London. We have a Dutch company which have delivered to the Schiphol Airport. And we have a Swedish-Korean company which have a test track in Uppsala in Sweden. We have a Skype Town system, JPod system, Mr. Megarail, STU, and Beamways, which I represent. And we'll take a look at Ultra and Vectus here. I can find the mouse pointer. There it is. This is the part of a promotional film for Ultra, and you can see it's animated, but now it's for real. So what they do have is a test track in Cardiff, and then they are building a real track in Heathrow right now. And this is their vehicle. And as you can see soon, this is just a small car. It doesn't have a special steel guideway. It runs on a concrete or tarmac. And the only thing that's new here, there's no driver. And instead you have a few lasers at the front which bounce off those curb sides there. So it's really a very simple system, and it's battery powered. And the only advanced thing about it is that they dock the battery or a connector to the guideway at the station. So they charge, whenever they're in the station, they charge the batteries. Still, it would be workable in a lot of situations, but not in a big city, because the batteries would not keep up with the load you would need to have. They would deplete during the day. And also we think at Beamways that this truck is very ugly, and it's around 2.2 meters wide for a single direction line. But it's workable. And here, of course, you can see the cars standing at the red light. There are no red lights because it's automatic control in a Podcar system. They've been approved for passenger transit in 2003 with a 4-second headway. Then we come to the Swedish project, which actually got me interested in this field. I read about they're starting to building this test track that you see now. And this has a steel track. It has a wheelbase switch, meaning that you have wheels which move up or down or something to make it go left or right in the switches. and it has linear motors in the guideway, which we think is a real big drawback. Here you can see the linear motors all the way. That costs a lot of money and costs a lot of copper to produce all those motors. It's around 20 times as many motors as if you would have them in the cars. But the good thing about linear motors is that you don't need traction on the wheels. You can have a slip. And here you can see, I think, the switching function. That's the motor. Now it comes later. Soon you will see the switching wheels. There you are. And now it's folded down for going this direction and goes outside the rail there. So it's reasonably safe, except if they stop in the middle, those wheels can be a bit problematic. This track is 1.3 meters wide, so it's a bit better than the Ultra track. Then we go to Skype Town, which is a more futuristic approach. They have a suspended design, as you can see in the top, and there's very aerodynamic shape of this vehicle, and it seats only two in this image. They also have a four-seater, more regular pod, but typically they would want people to ride in two-seaters because of the reduced energy use, which is in turn because they want to go really fast, 100 miles per hour. And they have maglev, no wheels, they say, but there are wheels anyway. And they have a linear motor. I don't remember if it's in the track or in the pod, but they also reinvented the magnetic switching from Aerospace Corporation somehow to go left or right without moving parts. And your neighbors with NASA Ames, and hopefully they will be able to build a test track in NASA Ames next year. And their guideway is only a half-meter wide, which I think is really good. So this is the system we are developing right now in Sweden. It's called the Beamways. It's also suspended design, but we stick to the wheels. We think maglev is a bit adding complexity to what's really already complex problem. It could be a future development, but what we did here is to allow the vehicle to tilt back and forth, which allows us to have very steep grades or slopes. And this in turn allows us to have the stations at the ground instead of up in the air, which is the normal case. And specifications, 50 kph, half-meter wide track again. And as you can see, normally double direction tracks. So we save some on not having as many poles, and we gain a lot in capacity. We have a regular rotating motor, no linear motor, and that's because we get traction inside, much safer inside the beam than if it would ride on top of something where it can rain or snow. So actually the wheels are inside the beam, not under the beam, of course. So why did I say that maybe something is happening on the marketplace? Because there are projects that's been ordered. 2 projects have been ordered, and 3 quotations. That's, we want the system, what does it cost? 3 cities, whereof 2 are really close to here. San Jose, Santa Cruz, and then it's a small town in Britain. And there are more coming up, Sweden, New York State. And the pictures are, this is a section of track from Heathrow being built, as you see, and this is a rendition of how it could look in Masdar in United Arab Emirates. Where it actually is going below ground because it's too hot for them to have on top. And that's it. It's built right now. So it's easier to go below ground if you build the track system at the same time as you build the rest of the city. So I just wanted to show you what could happen here at Google. This is the Google Earth image of the Google campus, and I added a little track system here. And I think you can see that this is the main office. Here's the Crittenden, and over here are other buildings down here. And there are 12 stations. This is a really dense network. Normally wouldn't build it maybe this dense, but to get a more interesting layout, I reduced the size of the circuits to 200 meters. We have 12 stations, 70 vehicles, 8,000 daily trips. That's a guess. I knew it was 8,000 working here, so maybe you do a trip to another house every other day or something like that. The mean trip length, the mean trip time, 2 minutes to go wherever you want to go, 1 kilometer. 15% have to wait. If you have 70 vehicles, with more vehicles, no waiting actually. So this looks neat, but is it possible from an economic standpoint? Yes, actually, it is. We have a cost here of $50 million to build all of this. And if you amortize that loan you took to build it, it's cost you $4 million per year or something like that. Operating cost just $1 million. $5 million per year. But if you have 8,000 trips a day, each saving 3 minutes of work time, and you have a cost here. I don't know if that's realistic, but if that's realistic, you save $6 million per year, and in total you save $1 million per year. So actually, it could be feasible. It would be a nice ride for you, I think. So my conclusions are, Podcars can be a very important solution to urban traffic, and I tried to show to you at the beginning that the other suggested solutions that people come up with, which are more of the same, basically, they don't really do the trick. And what we need in the podcar industry right now is examples. We need to show that this works. We need somewhere politicians and city planners can go and ride and see and feel this works. And of course, Google Campus would be a good place for such a demonstrator. Reasonable size system, still profitable, and through some arrangement, people could ride as a demo, we hope. That's all. Thank you very much. So, are any questions? Yes?
So, do you think this is a replacement for automobiles only in urban environments? Like, what about commuting from, let's say, the Google campus to San Francisco?
The question was if this is only a local facility. And I like to see it as local in the beginning. Going further would need higher speeds, and high speed needs more advanced technology. So we need to crawl before we can walk, but it's certainly thinkable. And if we had the technology now, when you have a $10 billion bill gone through for building a railroad, or was it even more, through California, you could build it much cheaper with this type of technology, and it would be a much better ride because you can go whenever you want. But we're not there yet. Yeah?
What about security, like denial of service? Somebody modifies a vehicle or something.
You mean denial of service in the networking sense?
Yeah.
I don't really know what that means. Isn't that? Sorry.
Basically Somebody just sabotaging the whole system by, I don't know, clogging a couple points on the network.
Yeah, that's possible. It's very easy to do that, actually. Just put your foot in the door. But the problem seems a bit overstated because that's not happening in metros or buses very much, if you look at it that way. The psychological way is, of course, someone will sabotage it sometime. But the thing you have, and I think we need here, is to compromise on the personal integrity bit and say that everyone needs to have a ticket which can identify you as the rider. And also I think we need to have camera surveillance, at least in the stations. Yes?
The cost slide that you showed, if you were to just kind of break that down into, like the infrastructure and the vehicle, what percentage would that be for the infrastructure and additional vehicles? And then how does that scale, from like a Google campus to like a city in the size of Mountain View, for example?
The question was regarding cost and if there's a breakdown into separate parts. And of course there is. We say that the guideway is around $8 million per mile, and stations are around $1 million each, and vehicles are a third of a million. No, sorry, that was in kroner, $50,000. When it comes to going to larger networks, it's a matter of how large is your city, because the usage comes when you cover a large percentage of the places you want to go. So in a large city, you need a large network to get that percentage of trips up. But on the other hand, if you have a lot of congestion, you're helped by that because people feel that it's really more useful. Maybe they go shopping in another mall because it has the Podcar connection. But there's no general answer. But it does scale, just like the road network scales. You could envision it as each guideway here having one lane of traffic at the 3-second headway level, which we're at right now. But I think we will get down to 1-second headways quite soon, and that would be 3 lanes of traffic for each guideway. And also with a 300-meter walk distance, if we allow that amount of walking, it would be very much sparser than the road network, of course. So it's like arterial roads in your mind, if you can have that level of distance between the guideways. And often it gets profitable for cities. Very large cities, I never did that calculation actually. Okay, there.
You didn't say anything about it, but I'm curious how this sort of system would compete with essentially some kind of guidance system that I can put in my existing car. It seems like with either small or no modifications to existing roadways, you might be able to have automated guidance with central control that would achieve some of these things, at least in part.
The question was regarding an ITS system, which is Intelligent Transport System, which actually is putting things in the car which prevents you from crashing, basically. And this is the only thing they do. They don't relieve you from congestion. Actually, you get more congestion because these tend to be more conservative than a human driver when it comes to distances between vehicles. So in San Diego, they did a test, and capacity went down when they installed the ITS systems.
Because they're not good enough cars then?
Just because you move the liability from the car driver to the manufacturer of the system, which means he's going to be very conservative with headways. So you get up to the 3-second headways that's, at least in Sweden, recommended for highways, although never actually used. You go 1 or 2 seconds normally. And you had a question?
You didn't mention how big the actual stations would be. Like, what would their footprint be?
Yeah, that's a good question regarding station size. stations can be dimensioned for the different size of need at certain points. For instance, at the rail station, you would need one large PRT station or even more than one. But in a local neighborhood, you maybe need very small station. And typically the station is just a sidetrack and a number of car positions after each other where people can load and unload. And this goes from 2 up to 20 or so. If you go above 20, you lose. It's a game of diminishing returns. Okay? One more?
What would be a typical fare rate that a user has to pay?
The fares are actually controlled by the operator, and it's a matter of how much the city is willing to pay or wants to gain, of course. I think the main issue could be if it's going to be a flat rate system or if you pay for each trip. Personally, I think you should pay for each trip because this is such a high level of service. You will get enormous effects of having a flat rate per month payment. I mean, that's what we're going to in the telecommunication business, but the cost for each telephone call is in reality very small. In this case, you actually have to move a piece of equipment every time, so you need to have a marginal cost in my mind. To recoup the operational cost would require you to have I don't have this number in US currency. It's gonna be 2 kronor per kilometer. It's gonna be 40 cents per mile or something to just cover the operational. And then you can maybe want to recoup for investment or maybe not. Okay? So if you have other questions, come up to me, and otherwise we're going to lunch now, so if anyone wants to join. Thank you.